This is Dr. Shankaraiah from Department of Physics. In last presentation, I have discussed about Module 4, which is magnetic and superconducting materials. In today's presentation, in this presentation also, I am going to discuss about the Module 4, in which I am going to discuss magnetic materials. The topic is classification of magnetic materials. So, on the basis of magnetic dipole moments, so yesterday we have discussed in the last presentation, we have discussed about magnetic dipole moments and the relations between magnetic induction, magnetic field, magnetization and susceptibility, permeability, so on. Many definitions we have discussed in the earlier presentation. So, based on this magnetic dipole moments, it has been found that the solids can be divided into two broad groups. Okay, so based on the magnetic dipole moments, solids are classified, or the materials are classified into two broad categories. Okay, so the first one is the atoms of one group do not possess permanent dipole moments. Okay, so based on the magnetic moment, the solids are classified into two categories. The first category or the first group is materials which do not possess permanent magnetic dipole moments. So this is one group, and the second group is the materials which have permanent dipole moments. Okay, so based on the magnetic dipole moments, solids are classified into two categories. The first category is the materials in which the atoms have permanent dipole moments, and the materials in which the atoms do not have permanent dipole moments. So these are the two broad categories that are classified based on the magnetic dipole moment present in a material. So first category or the first group is materials without permanent magnetic moments. So materials which do not have permanent magnetic dipole moments, the examples of this group is diamagnetic materials. So the diamagnetic materials do not have permanent dipole moments. Okay, so diamagnetic materials are the materials consisting of atoms with zero magnetic dipole moment. Okay, so this is the first group in which atoms do not have permanent magnetic dipole moments, and the example of this group is diamagnetic materials. And the second group is materials with permanent magnetic moments. Okay, so the first group is materials without permanent magnetic moment. Diamagnetic materials are the examples which do not have any permanent magnetic dipole moment. In the second group is materials with permanent magnetic moment. Okay, so in this group, based on the interaction of permanent magnetic dipoles, the second group is further subdivided into four groups. Okay, so now we are saying that materials are having permanent magnetic moment. Okay, so again this group in which materials have permanent magnetic dipole moment, based on the interaction between the permanent magnetic dipoles. Again, this category is classified into four subgroups. Okay, so whether the interaction, what kind of interaction do the permanent magnetic dipole moments have? Based on the interaction between these permanent magnetic dipole moments, the materials with permanent magnetic dipole moments are again subdivided into four categories. So the first one is paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. Okay, so these are the four subcategories in materials with permanent magnetic moment. So paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So these are the four subcategories in materials which do have permanent magnetic dipole moments. So let us see what kind of interaction do the permanent magnetic dipoles have in these four different categories. First, if the interaction between the atomic magnetic dipoles is negligible, then that material is called paramagnetic material. So paramagnetic material has permanent magnetic dipole moments, but these permanent magnetic dipole moments, the interaction between these magnetic dipoles is negligible. The interaction is very weak. so that you can neglect the interaction between these magnetic dipoles, and then that material is called paramagnetic material. Okay. So the next one, if the magnetic dipoles interact in such a way that they tend to orient in the same direction, magnetic dipoles interact in such a way that all the dipoles orient in the same direction, then that material is called as ferromagnetic material. The interaction between the magnetic dipoles is such that all the dipoles will orient in the same direction. Then that material is called ferromagnetic material. Okay. And if the neighboring dipoles orient in opposite directions and if the dipoles are of equal magnitude, then that material is called antiferromagnetic material. So in antiferromagnetic materials also there is a strong interaction between the magnetic dipoles, and they orient in neighboring atoms orient in opposite directions. So one is up, one is down, one is up, one is down, one is up, one is down. So they orient in opposite. The neighboring atoms are oriented in opposite directions, and the magnitude of this magnetic dipole is same. All the dipoles are going to have the same magnitude. Then that material is called as antiferromagnetic material. If the neighboring dipoles are of different magnitude and orient anti-parallel, the material is ferrimagnet. If the neighboring dipoles are of different magnitude and they orient in anti-parallel, like the ferromagnetic, antiferromagnetic materials, here also the magnetic dipoles orient in, the neighboring magnetic dipole orient in opposite direction. But the magnitude of the dipoles are of different, okay. So one is long and the other one is short, long, short, long and short, like that. So the magnitudes are different here, and then that material is called ferrimagnetic material. Okay. So here in paramagnetic material there is no interaction. The interaction is very strong, so they can have random orientations. There is no interaction, so all the magnetic dipoles are oriented in random way. That is the reason why this material is called paramagnetic material. In ferromagnetic material, the interaction is strong and they all orient in the same direction with all dipoles having equal magnitude. And in antiferromagnetic materials, the neighboring dipoles orient in opposite directions and all the magnetic dipoles are of equal magnitude. In ferrimagnetic materials, the neighboring dipoles orient in opposite direction, but the dipoles are having different magnitude. Okay. So then that is ferrimagnetic material. So these are the four magnetic materials. These are subcategories in materials with permanent magnetic dipoles. So here is a picture of these four magnetic materials. So here it is paramagnetic material. Paramagnetic material. So here the interaction is weak. So here interaction between the dipoles. Interaction between the dipoles is weak. That is the reason why they orient in random directions. So this is ferromagnetic material. This is ferromagnetic material, and the interaction between the dipole is strong. Interaction between the dipoles is strong, and that is the reason why all the dipoles are oriented in the same direction: paramagnetic, ferromagnetic, and antiferromagnetic. So this is antiferromagnetic material. So here also interaction between the dipoles is strong. Interaction between the dipoles is strong. Okay. And interaction between the dipoles is strong, but the neighboring dipoles are oriented in opposite. One is up and down, up and down, up and down. And all the dipoles are having equal magnitudes. The magnitude of these dipoles, these dipoles, these dipoles. All the dipoles are having same magnitude in ferromagnetic and antiferromagnetic and paramagnetic, but paramagnetic there is no interaction. Interaction is very weak. Now coming to the ferrimagnetic material. So ferrimagnetic materials. So these ferrimagnetic materials, interaction is strong, and all the dipoles are oriented. I mean, the neighboring dipoles are oriented in anti-parallel direction, but here only the difference with antiferromagnetic material is that the magnitude of these dipoles is different. So this is longer, this is smaller, longer, smaller, longer, smaller. So the magnitude of the dipoles is different. Here the magnitude of dipoles is equal. Okay, so maybe I'm writing here. So maybe I should write here. Yeah, fine. So magnitude of dipoles is equal. Here also magnitude of dipoles is, this is antiferromagnetic magnitude. So magnitude of dipoles is same. Here magnitude is different. Magnitude of dipoles is different, not same. It is different. Okay. So the magnitude of the dipoles is different in ferrimagnetic materials. So these ferrimagnetic materials, the magnitude of the dipoles, okay, the magnitude of this dipole and this dipole is different. Okay, the magnitudes are different. So these are the four categories of the magnetic materials that come into the second group, in which materials with permanent magnetic dipoles. Okay, paramagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic material, and the last one is ferrimagnetic materials. So these are the four subgroups that come under materials with permanent magnetic dipoles. So let us look into the differences between these magnetic materials, differences between dia, para, and ferromagnetic materials. Okay. So what are the differences between these different types of magnetic materials? The diamagnetic materials. Diamagnetic materials, it is a property of the material which has repulsive nature and opposing magnetization. So if you apply any magnetic field, these diamagnetic materials are going to repel the applied magnetic field. So diamagnetic materials are going to repel the applied magnetic field, and they are going to oppose the magnetization. And paramagnetic material, it is a property of the material which has weak attractive force. So paramagnetic materials have weak attractive force. It is a property of the materials which has strong attractive. So ferromagnetic materials have strong attractive force, whereas diamagnetic materials oppose the applied magnetic field, and paramagnetic materials have very weak attraction to the applied magnetic field. The property is due to orbital motion of electrons. So the diamagnetic materials, this property is due to orbital motion of electrons. Okay. So that is due to diamagnetic material property is due to the orbital motion of electron, whereas paramagnetic material property is due to spin of electron, and ferromagnetic material is also due to spin of electron. Both para and ferromagnetic materials, the property of magnetization is due to spin of electron, whereas the diamagnetic materials, the magnetization is due to the orbital motion of electrons. In diamagnetic materials, there is no spin, whereas in paramagnetic material, spin is random, and ferromagnetic material spin is parallel. So here no spin at all. Here spins are there, but they are in random directions. So no orientation, random. They are oriented in random way. So here all the spins are parallel. All the spins can orient in up direction, or all the spins can orient in down direction. So all the spins are parallel in ferromagnetic materials. These materials, the diamagnetic materials, are lack of magnetic dipoles. So we have discussed, when we are discussing about the materials with permanent and without permanent magnetic material, we said that materials without permanent magnetic moments or examples are diamagnetic materials. So these diamagnetic materials do not have any permanent magnetic dipoles, whereas paramagnetic materials do have permanent magnetic dipoles. dipoles, and ferromagnetic materials also do have permanent magnetic dipoles. Okay. So these are some of the difference, and we will discuss some more differences between these dia, para and ferromagnetic materials in the coming slides. Okay, so this is diamagnetic materials. So diamagnetic materials do not possess permanent magnetic dipole moment, and hence spontaneous magnetization is zero. Spontaneous magnetization means without applying magnetic field also materials can get magnetized. That is called spontaneous magnetization. So spontaneous magnetization is spontaneous magnetization. What do you mean by spontaneous magnetization? Magnetization of a material without applied magnetization of a material without applied magnetic field. Without applied magnetic field. So even though we are not applying magnetic field, material can get magnetized. So that magnetization is called spontaneous magnetization, right? So these diamagnetic materials do not have any spontaneous magnetization because they do not possess any permanent dipole moments in them. Okay, whereas paramagnetic materials possess permanent magnetic dipole moment, but there is no spontaneous magnetization in the absence of external field due to random spin. Because here in diamagnetic materials there is no spin at all, but in paramagnetic materials there are spins, but they are all oriented in random directions, right? So here all the spins are oriented in random direction. So without applied magnetic field, you don't get any magnetization. So the spontaneous magnetization is zero. Coming to the ferromagnetic material, they possess permanent magnetic dipole. Ferromagnetic materials. So this is paramagnetic material. This is para and this is ferro. And this is dia. Okay, so ferromagnetic materials possess permanent magnetic dipole moment. Also, in the absence of field, they have spontaneous magnetization in the absence of external field due to parallel spin. In these ferromagnetic materials, the spins can orient in the same direction even without applying magnetic field. Okay, so that is the reason why these ferromagnetic materials do have spontaneous magnetization in the absence of external field. So spontaneous magnetization, ferromagnetic materials do have spontaneous magnetization, para do not have and dia also do not have. Okay, and the reasons we have discussed. The relative permeability mu r is less than 1 for diamagnetic materials, whereas the relative permeability is greater than 1 for paramagnetic materials, and also very large for ferromagnetic materials. Okay, so here we can see the material is repelling the applied magnetic field in diamagnetic material, whereas para there is a partial transmission of these magnetic flux lines, but in ferromagnetic material there is a clear transmission of these magnetic flux lines through the material. Okay, so that is the permeability is less than 1. Permeability is negative for diamagnetic materials. That is why they repel the applied magnetic field. And whereas paramagnetic material, it is positive and small, but ferromagnetic material, it is positive and large. Some more properties or differences between dia, para, ferromagnetic materials. So in diamagnetic material, the susceptibility is small and negative. This is diamagnetic material. So the susceptibility is small and negative. For paramagnetic materials, the susceptibility is small and positive. So for para, the susceptibility is small and positive. And for ferromagnetic material, susceptibility is positive and large. Okay. So that is susceptibility. Small for dia, small and negative for dia. It's important. Small and positive for para and small and large for ferromagnetic materials. Chi does not depend on temperature. For diamagnetic materials, so no particular graph is so there is no dependence of susceptibility on temperature in diamagnetic material. Whereas paramagnetic materials, susceptibility depends on temperature. So this is the behavior of susceptibility. So this is chi versus T. So as you increase your temperature, the susceptibility is decreasing in paramagnetic material. This is ferromagnetic material. So chi, so there is above a critical temperature, only above critical temperature, the susceptibility decreases with temperature. So this is in ferromagnetic material. And the susceptibility does not depend on temperature in diamagnetic material, and in paramagnetic material there is a dependence, and the chi is equal to C by T, which is Curie's law. And in ferromagnetic material, chi is equal to C by T minus theta, where theta is the Curie temperature. So this is called Curie-Weiss law for ferromagnetic materials. Diamagnetic materials do not exhibit the phenomenon of hysteresis. So diamagnetic materials, no hysteresis. Paramagnetic materials also do not exhibit the hysteresis, whereas ferromagnetic materials do exhibit hysteresis. So you can see the hysteresis in ferromagnetic materials. You cannot see the hysteresis in dia and paramagnetic materials. Only ferromagnetic materials exhibit the phenomenon of hysteresis. And the examples of dia, para and ferromagnetic materials. So diamagnetic materials examples are copper, zinc, H2O, some of the examples, organic materials. And also organic materials in diamagnetic materials. And ferromagnetic materials, aluminum, manganese and some other materials are examples. In ferromagnetic materials, transition metals are examples, which are iron, nickel, cobalt and so on and so forth. These are the examples for ferromagnetic materials. Okay. So in this presentation, I have so just summarize this presentation. So in this presentation, I have discussed about the classification of magnetic materials. Classification of magnetic materials based on magnetic moment. Okay, so I have divided, we have discussed that the materials, solids are classified into two categories based on the magnetic moment. So the first one is with materials with permanent magnetic moment, materials with permanent magnetic dipole moments, permanent magnetic dipole. The second category is materials without permanent magnetic dipole moments. So based on the magnetic moment, materials are classified into two categories: materials with permanent magnetic dipole moments and materials without permanent magnetic dipole moments. And then we have discussed that materials without permanent magnetic moments, diamagnetic materials are the examples, and materials with permanent magnetic moments again subdivided based on the interaction between the magnetic dipoles into four categories. So the four categories are paramagnetic materials. So materials with permanent magnetic moments again subdivided into para, ferro, antiferro and ferrimagnetic materials. Okay, so and then we have discussed the differences between these dia, para and ferromagnetic materials. Differences are properties of these three different magnetic materials. Okay. So I am ending here this presentation here. In the next presentation, I will discuss about the hysteresis. We have discussed in the previous slide that some of the materials, magnetic materials, exhibit the phenomenon of hysteresis and some materials do not exhibit the phenomenon of hysteresis. So in the next presentation, I will discuss what is hysteresis and how these materials exhibit hysteresis. Okay. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.